Hello everyone. Have you ever tried to push a door open by pressing right next to the hinge? It hardly moves. But push at the outer edge, and suddenly the door swings easily. That effect, the turning influence of a force, is what we call torque. Mathematically, torque tau is defined as the cross product of position vector r with force F. Tau equals r cross F, equation 6.23. Its magnitude is r times F times sine theta, where theta is the angle between r and F. So torque isn't just about how strong a force is. It also depends on where and how it's applied. That's why a small push at the right place can rotate a heavy door. Another way to look at torque is through the idea of the lever arm. Torque equals the force multiplied by the perpendicular distance from the axis. So tau equals r perpendicular times F, equation 6.24b, or equivalently, tau equals r times F perpendicular, equation 6.24c. Notice torque becomes zero if the force acts exactly through the pivot or if the perpendicular distance vanishes. That's why pulling on the hinge of a door doesn't rotate it at all. The lever arm is zero. Now, let's flip the picture. Just as torque is the rotational analogue of force, angular momentum is the rotational analogue of linear momentum. For a particle of mass m at position r with momentum p, its angular momentum L equals r cross p. The magnitude is r times p times sine theta. We can also write L as r perpendicular times p, or as r times p perpendicular. And if the line of momentum passes through the pivot, angular momentum vanishes. This makes sense, no turning influence about that point.
Now comes a beautiful law, the rotational version of Newton's second law. Differentiate angular momentum with respect to time and you get torque. In symbols, dl by dt equals tau. This means the torque acting on a particle is exactly what changes its angular momentum. Just like in translation, force equals rate of change of momentum. In rotation, torque equals rate of change of angular momentum. This is the foundation of rotational dynamics. Of course, real bodies are made of many particles. So for a system, the total angular momentum L is the sum of all Li, each equal to Ri cross Pi. Similarly, the total torque is the sum of all Ri cross Fi. But here's the trick. Internal forces cancel in pairs thanks to Newton's third law, so only external forces matter. That leads to the general law, dl by dit equals external torque. That's equation 6.28b. It tells us the angular momentum of a system changes only if an external torque acts. Now suppose the external torque is 0. Then dl by dt equals 0, which means angular momentum is conserved. In other words, L remains constant in both magnitude and direction. In component form, Lx, Ly, and Lz are all constants. This conservation law explains why a spinning skater pulls in her arms and spins faster. The moment of inertia decreases, so angular velocity increases to keep angular momentum constant. The same principle governs planetary orbits and even pulsars spinning in space.
Let's try some examples. Example 6.5. A particle at r equals I hat minus j hat plus k hat is acted on by a force F equals 7 I hat plus 3 j hat minus 5 k hat. Torque is r cross F. Using the determinant method, we compute the vector components to find tau. Example 6.6. Show that a particle moving with constant velocity has constant angular momentum about any point. Here, L equals r cross mv. Its magnitude equals mv times r sine theta, which remains fixed since the perpendicular distance is constant. The direction is perpendicular to both r and v. So angular momentum is conserved. These examples prove torque and angular momentum are not abstract. They are measurable and calculable in real systems. So to wrap it up, torque is the rotational analogue of force defined as r cross F. Angular momentum is the rotational analogue of linear momentum. defined as our cross P. Their link is captured in the law dL by dt equals tau, or for systems, dL by dt equals external torque. If external torque is zero, angular momentum is conserved, explaining the spins of skaters, the stability of gyroscopes, and the motion of planets around the Sun. I hope this gives you a clear and confident grasp of torque and angular momentum, two pillars of rotational dynamics. In the next session, we'll build on this and explore how these laws apply to rigid bodies in motion. See you then.